So as it's Friday, I thought we might start a little bit more relaxing than the past presentations. So I brought along a couple of pretty pictures for you. And the only question I have is please look at them thinking of what if you were at the point where the camera is, where does the moisture come from that you feel? So first of all, picture from New York City. So just imagine, where is the moisture coming from? Like what surface is in this picture? And if you look at a picture like this, I mean, it's definitely a very different urban setting. So you have different sources of moisture. Or a picture like this, where all the green is almost gone. And I think what immediately becomes clear if you put these next to each other is that one, they're very different, and two, they're not homogeneous, and three, which is also very important, they consist of different surfaces. Urban surface is not one surface, it's a combination of different ones. So what I want to do today is reconstruct the urban evaporation, because that's actually what you would feel moisture-wise if you were to point the camera. And in order to do that, we're going to use eddy-covariance observations, in this case from Berlin, which you can see in the background, 2 sites. And we'll look at land cover contributions, so the different surface types. And just going back to that picture for a moment, I reckon you've all seen that there's quite a bit of impervious area. Maybe not too much moisture there. More moisture might come from the high vegetation. Or low vegetation, mind you, this is actually artificial grass, but just imagine it's real grass. I couldn't find any realistic grass here. Or open water. So these are the 4 surface cover types we're going to use today. So keep in mind these colors, they'll keep coming back. And what's very important is we look at the footprint. So eddy-covariance doesn't measure at a single point, it measures a source area. And this is just an example of a footprint at a given time with quite strong winds, but in another moment we might have a footprint that looks like this. And I think you can already imagine this does something to the moisture you would feel. What we do a lot of times is we actually assume that we get the surface cover from within a radius of 500 or 1,000 meters. But as you can already see from just this example footprint, this is actually not very realistic. So, to the 2 sites. The first one is in the suburbs of Berlin, Rotenburgstrasse, and it's pretty well, there's quite a lot of vegetation, and it's got a really nice 40-meter tower. And we only use the top eddy-covariance here. And for the more urbanized side, it's at the top of the Berlin campus, and it's a bit more densely built, but which you can already see very clearly that this Tier Park, if you are familiar with Berlin, quite a big park, is actually right next to the eddy-covariance tower. And if you compare them, it becomes very clear that one is way more urbanized than the other. Cool. This shows the contribution of the different surface covers to the footprints at any given time for 1 year. What you can already see is that if we use a constant value, that's not very realistic, maybe except for the water at the Rotenburgstrasse, but because there's virtually none. But we see bimodality at the Rotenburgstrasse, especially for impervious and for the high vegetation. And especially want to show you the impervious surfaces at Berlin campus. There's a range of 50% there. So assuming the values of that radius, it's just not even true most of the time. So that's why we're going to look at it at a footprint basis, so for every time step. Having said a lot about footprints, let's get into these different surface cover types. How do we represent those? So for each, we've got a different methodology to relate that small scale surface to that eddy-covariance. And the first one, impervious surface, we just imagine roads and roofs as a straight line with dents in them. And the only fancy thing we do to those dents is we make them tapered because we expect there to be more space for water if the water depth is a bit higher. But this is in the order of magnitude, maybe 1 millimeter. And this conceptual model does 2 things. It fills up with rainfall and it dries with the evaporation. It's not more complicated than that. For high vegetation, we actually don't use any conceptual modeling because we have some very nice observations in Berlin. So high vegetation is mainly trees, and what we have from those trees is subtle observations on an hourly basis. The only downside of these observations is they're not that reliable in magnitude, so we don't want to use that. So what we actually do is we scale them with the daily soil moisture loss. So a reliable estimate of the magnitude and a reliable estimate of the daily trend. Well, we also need some interception, so we use the Rutter model for that one because it's capable of hourly resolution. For low vegetation, I'd say we might even go simpler, because if you're at Steglitz and you look, there's like at the bottom there's only low vegetation, and in the back there's a nice eddy-covariance that only observes this part. So you can just directly use the eddy-covariance observations. And for open water, we use Panman. Mind you, this is not Panman Monteith, there's no vegetation in this, there's just Panman. So, all in all, we've got a very simple conceptual model for our impervious area, some combination of observations on trees, eddy-covariance, and Panman. And what we then can do is if we use those four surface cover types and their dynamics, and we sum them weighted by their contribution to the footprint, we should be getting that eddy-covariance signal we're after. And if you look at that for Rosenbroekstrasse, so we've got the reconstructed versus the observed, there's quite a lot of spread, but for the latent heat flux, this is actually not too bad. This is within the same realm as the urban surface models before. And it actually becomes a little bit better even if we look at the theory campus. We actually lose our bias. We do still have some spread, but we're actually quite happy with what we're seeing. And what this allows us to do is to look at all these evaporation dynamics separately. So first thing is on the left of every pair, you see these squared bars, and they are the contribution to the surface cover. So for Rosenbroekstrasse, the impervious area, it's about 40%. The other bar indicates how much they contribute to the latent heat flux. And as you can see, that's not even 10% for the impervious area. While at the same time, the high vegetation is surface cover-wise almost as much, but it has almost 80% of the latent heat flux. So you see that the different surface cover types are very different in the total amount they evaporate. And what's nice to see, the urban campus, it just does more or less the same. The only difference is that we do see a little bit of open water evaporation, but that also contributes more than its contribution to the surface cover. Well, to look into this a bit more detail, I've looked at the dry down in 2019. So just before this, we've got a rainfall event. And what we see is that over time, latent heat flux seems to go down, which makes sense. You get water limited, but it's pretty hard. This is what's also what was really weird to me when I first saw this is why is suddenly open water evaporation only becoming a thing after a couple of days? And that's simply because the wind direction changed. There was no water in the footprint. So to make this a bit easier and actually look at the surface cover dynamics separately, we can just set it to 100% of one surface cover type because we have that data. And then you see that the latent heat flux from the impervious areas is this huge peak, and after that there's nothing. Which you can imagine, like if you see a rainfall event on the road, there's a lot of water, but actually after a few hours most of the time, the road is dry. For low vegetation, it's actually quite surprising that it doesn't really seem to have a dry down, which might have to do with the fact that there's no water limitation yet. This one's a bit hard to see, I see, on this screen. But anyway, what you can really clearly see is that the trees start limiting their evaporation already quite rapidly after the rainfall event. And as you can see, we do not have data for the Panman calculation at all times, but you see this nice daily trend. And what you also see is that there's not really a relationship with rainfall, which you might not expect as well, because there's never water limitation in an open waterway. And the reason it goes up a bit is because the temperature changes a bit. All in all, we can look at the surface cover contributions, and we need to look at footprints because what we measure with eddy-covariance is just simply not constant. If we split the surface cover into 4 different types, we can actually model or observe this pretty well and get back to that overall flux we observe with the eddy-covariance. And then we see that it's very different per surface cover type. Thank you.
Questions? No questions?
I can. However, in your conceptual thinking, there's no grass under the trees, or there is.
No, there's not. And I think for most of the cases, it's a fair assumption because it's either street trees in Berlin, which typically have the purchase area underneath them, or you might have some gardens where there's a little bit of grass, but it's not too much. It would also show up in the soil moisture loss, so then we would just scale it as being part of the tree. So like the same amount of water would evaporate.
Okay, I think we have time for one more question.
Yeah, thank you, very nice work. I was wondering if your source area model, your footprint model, how do you account for the variability as well in roughness? I know at least the central site has quite some high-rise buildings in the area. How did you overcome that challenge?
Yeah, so what we actually do is we do use the eddy-covariance observations to light these. There's also an estimation in that of the roughness, so we use that. And other than that, we at this moment are not looking into this. What we are planning to do is also try with LES to reproduce this as well, and there you would definitely see that effect.
Okay, thank you again.
Thank you.